Although the Taylor series is useful to estimate errors, exactly how it is used in numerical methods might not be clear to you. So let's explore this and further our understanding by looking at our dear old falling parcel example. So we saw early on that we could approximate the velocity function using the Taylor series approximation, that is the velocity at the next time step, v of t at I plus 1, is equal to the velocity at our current time plus the derivative, first derivative multiplied by our time step plus some remainder term. Now we can rearrange this, so let's do that. So we can say the derivative, the first derivative at our current time step is equal to the velocity at our next time step minus the velocity at our current time step divided by the time step minus our remainder term divided by our time step. Now, from our Taylor series approximation, you know that the first term on the right side of the equation, so that is this term, is known as the first order approximation, and our error term here, R1 divided by delta t, is known as the truncation error. So we can rewrite what our truncation error is, that is R1 over delta t is equal to the second derivative at this value epsilon divided by 2 factorial multiplied by delta t. We say that it is equal to our first order approximation truncation error, which is equal to an error term of order of our time step. So you can see that here. It's proportional to delta t. Now I want you to notice something. I've actually dropped the power term of in our truncation error, and that's simply because we're dividing by our time step delta t. So the estimate of our derivative has a truncation order, or truncation error, of order of magnitude that is in relation to our time step. And so if we halve our time step, we will halve our error.